Hi, I'm Helium Foundation grant recipient Nicholas Lopez. I'm here to talk about how Helium and LoRaWAN have been useful tools for my weather collection company, Conda Weather.
Every day, National Weather Service stations launch weather balloons from 900 global locations to collect critical weather observations above the Earth's surface. These balloons, also known as radiosondes, send temperature, pressure, humidity, and GPS coordinates as they continuously ascend into the atmosphere. The data is critical for global weather forecasting and remains the most reliable method to measure moisture at mid-level altitudes. However, radio receiving technologies at many of the stations in low-income countries has not been upgraded in the past 20 years. Additionally, the amount of helium gas needed to get the balloons off the ground has become prohibitively expensive, even for U.S. Weather Service offices, a number of which have suspended collection activities due to the shortage. Here we introduce a smaller, more lightweight, and lower-cost IoT technology that can improve, and in some regions outright replace current radiosonde stations up to 35,000 feet. The small size means that much less lifting gas is needed, and the open-source nature of the project means customers in developing countries can 3D print them as needed. A traditional National Weather Service radiosonde station consists of an expensive high-gain rotating antenna that rotates to the direction of the balloon to receive the radio packets. In developing countries, this involves a high capital cost in need of maintenance, in addition to the already high costs of helium gas. We can dramatically reduce these costs by using 90% less helium, a modern GPS receiver for deriving wind speed and direction, and a crowdsourced approach to receiving the data over towns and cities. Instead of relying on a single antenna, Conda is using the Helium network to crowdsource the receiving of the data packets using hotspots underneath the balloon as it passes overhead. A rising weather balloon maximizes the line-of-sight abilities of LoRaWAN, as there are fewer and fewer ground obstacles that may reduce the signal strength. Effectively, the balloon becomes more and more like a small satellite with an enormous footprint to communicate with tens, if not hundreds, of helium hotspots on the ground. The balloons only need to reach 35,000 feet to capture the layers of the atmosphere that are responsible for 95% of day-to-day weather patterns. The Helium network's single packet range of 10 kilometers and hotspot redundancy helps compensate for the balloon's natural drift away from the launch location and adds extra reliability when the balloon's radio signals need to pass through clouds or rainy weather. This is a big reason why LoRaWAN is the preferred technology over LoRa, and why Helium is a great network to support this data collection. Just like traditional weather balloons, these new data collection methods have enormous implications for weather forecasting in developing countries. Unlike most agricultural companies in the United States, the agriculture industry in low-income regions largely consists of what are known as smallholder farmers that farm a very small 5-hectare plot of land. Work on the farm is usually done by family members and neighbors, which makes harvesting the crops a relatively fast operation. This means that a short-term rain forecast could be extremely valuable to farmers, given an adequate warning notification system. Also, unlike rainfall in the United States and Europe, which can be complex in nature, rainfall over tropical locations is mostly dependent on the amount of moisture directly overhead and near to a specific location. This small scale and precise nature of this phenomena makes satellites not the best fit for measuring this three-dimensional information. Instead, sampling the air directly with radiosonde can provide the level of detail needed to make a site-specific rain forecast. With this in mind, we've built an initial machine learning model that will make an extreme rain or no rain forecast over a short 12-hour time frame. The initial model was trained using data from over 1,000 weather balloon launches in Douala, Cameroon over the past 12 years. Even with a rudimentary model, the results were moderately successful, potentially outperforming current weather service forecasts for the city. When used with the real-time data collected with the low-cost deploy-anywhere solution, this type of modeling has the potential to make an impact for hundreds of small cities in West Africa and tropical climates that are underserved with poor rain forecasts. Due to the incredibly low costs needed to acquire this data and make a forecast, we think there's commercial viability of a network where paying customers include construction companies, flood insurers, and government agencies. Here's our partner, Betty Huertero, speaking with the Telos Foundation.
I got the opportunity, I was honored to be elected to the board of a company called WECOL Limited, and WECOL is a green energy developer. Basically, they focus on biomass production, and they focus on this using energy crops. So my work with them was basically to utilize the technology, apply blockchain solutions to streamline the operations and to make sure that the system has zero waste.
Kenya-based company WeCall needs to know the current rain forecast to know if the soil of their crop, DRG grass, will be oversaturated in the near future. Because they are a B2B company, a flooding event could have downstream impacts on their customers that utilize the biomass energy they provide. Similarly, companies with solar assets need to know if rainfall is imminent so that they can alert downstream customers of reduced solar outputs during the rain event. While developing countries would be our primary market, there's an advantage to monitoring West African weather and climate in particular. West Africa may seem well removed from the United States, but the Atlantic waters just offshore the African coast happen to be a critical region in the science of forecasting hurricanes in the East Atlantic. In fact, as many as 80% of major hurricanes that threaten the U.S. coastline begin their journey as tropical waves moving west over Africa. Hurricane Irma in 2017 formed off the coast of West Africa and caused $77 billion in damage to the Caribbean islands and Florida as it tracked across the Atlantic Ocean, making it the fifth costliest cyclone in history. The West Africa region is so important to hurricane formation, in fact, that NASA funded a multi-year campaign known as the African Monsoon Multidisciplinary Analysis in 2006 to improve weather data collection in the region. These observations consisted of an improved weather balloon network, aircraft samples, and LiDAR measurements. While there was no published result that found a direct link between hurricanes and radiosondes due to the lack of data even after NAMA, several journal articles stated that the additional weather balloon observations were helpful in determining the initial state of the atmosphere for numerical weather models. This, of course, is the first step to improved weather forecasting over the region and just offshore. Additionally, one study found that for the first 24 hours, the radiosun observations actually have direct downstream benefits to weather forecasting in southern Europe.
The dearth of high-quality observations in the region is exactly what makes each weather balloon observation so rare and valuable. It would take only 20 well-maintained upper-level stations to replace the current weather balloon network operated by government entities in West Africa. Additionally, when launched from islands or ships in the Caribbean, the wind data from the radiosondes could almost certainly have a bigger impact on hurricane forecasts. Even marginally better forecasting of Atlantic hurricanes in the 7 to 14 day time frame could save agencies like FEMA tens of millions of dollars per year in disaster relief.
After the NAMA program completed in 2008, scientists concluded that the best way to reverse the trend of the degraded radiosonde network would be to establish a new network, independent of government agencies with direct contracting payments to individuals for preparing and launching the weather balloons. Condo Weather is taking this call to action seriously and using the global nature of blockchain to achieve only what multinational corporations and governments could do in the past.